So this is our third lesson on circle theorems now. And this lesson is going to be focusing on the theorems about tangents of a circle. Okay, so let's jump right in. So first of all, let's discuss what a tangent line is. Okay, so if we were to draw a line through a circle, it would touch the circle, or it would meet the line of the circle at 2 points. Okay, if we draw a line a bit closer to the edge of the circle, it would still touch the 2 points, but those 2 points are getting close together. If we move that line again to the edge, the points are getting closer and closer together now, until eventually you would draw a line that is at the very edge of a circle, that it only touches the circle at 1 point. Okay, and this is called a tangent line. Okay, so this would be a tangent line. And that is a line that only touches a circle once. Okay, so just like the last circles, if you draw a line anywhere through a circle, it will always touch it at 2 points, apart from the tangent line, which only touches it once. Okay, so that's a really important fact to know about tangent lines. Now, the first circle theorem for today is a tangent to a circle is perpendicular to the radius drawn to the point of contact. Now, what that means in simple words, the angle between a circle's radius and a tangent is always 90 degrees, okay? So that's what the word perpendicular means. It means 90 degrees too, okay? So what this rule basically says is where a tangent meets the circle, if you draw a radius from the center of the circle to that point, that angle is always 90 degrees, all right? And you can see if we were to draw different tangent lines and you always draw the appropriate radius, the angle will always be 90 degrees, okay? So let's have a look at answering some questions. Now we know this rule, let's have a go at answering some questions. So we're told that the line AB is tangent to the circle. The angle of OCD is 38 degrees. So I can see the points O, I've got points O, C, and D, and the angle in between them is 38 degrees. So I'm given 38 degrees. I'm asked to find the angle BCD. So I've got B here, C, and I've got D. So I'm trying to find this angle here. Okay. And I'm only told 38 degrees is the angle apparently just next to it. Okay. But if we remember, the first circle theorem is a radius line drawn to a tangent will always be 90 degrees. So I can with certainty draw a 90-degree symbol here, because I know the angle between the radius and this tangent is going to be 90 degrees, okay? So therefore, to answer this question, I'm trying to find angle BCD. I know that angle BCD plus 38 has to equal to 90 degrees, okay? Because both those angles, to add together, they will make that right angle in the corner, okay? So therefore, to find BCD, just rearrange the equation. BCD equals 90 degrees, take away 38 degrees. BCD equals 52 degrees, okay? That's your final answer. Now, obviously, that's quite easy, so we're going to add a bit more complexity to these questions. So let's have a look at a slightly more complex example. Okay, so got a new set of lines here. So this time the line AB is tangent to the circle, same as always, and the angle of BCD is 63 degrees. So we can see we've got that on the diagram there. We've got an angle of 63 degrees. Now we're asked to find the angle OED. Okay, so O is here, OED. So what we're trying to find is this angle here, the angle at the nook of E, okay? So how can we start this? Well, as we can see, looking at the top again, we've got a lovely radius joining to the tangent. So I know for a fact that this angle is already going to be a radius, okay? So if I want to draw this other angle here now, I know that this angle, this purple angle, plus 63 has to equal to 90. So something plus 63 is 90, so that's going to be 27 degrees, okay? Because I know those two angles together have to be a right angle. Now, a rule from a previous lesson, because we can see we've got a line going straight through the circle. So we've got a semicircle, but we can think of this as being, this is a diameter line, so we've got a semicircle on this side. If you draw a triangle in a semicircle sorry, it will always be a right angle triangle. So I know for a fact that this angle here is going to be a right angle, okay? So therefore, now if I'm going to find this OED angle, green angle, I use what I'm given. So all triangles add up to 180 degrees. So angles in triangles equal 180 degrees. And my angles are, well, I've got my OED at the bottom. So OED plus 27 plus 90 equals 180 degrees. So OED plus 117 equals 180. OED equals 180, take away 117. OED is equal to 63 degrees. Okay, and that's your final answer. So it's using the same, just using the initial rule that angles to a tangent are always a right angle. And we're just starting to throw in a few of the older rules that we learned from the last couple of lessons, okay? Let's look at one more example. So third example now for this first circle theorem of the lesson. So we're told that the line CD is tangent to the circle and that the angle of ADB is 55 degrees. So we're given angle ADB there, 55 degrees. And we're also trying to find angle BAD. So let's find that on the diagram. We've got point B, A, and D. So angle BAD will be in the nook of A. And then we're also trying to find angle BCD, okay? So we've got B, C, D. So our angle is going to be in the nook of C, okay? So let's crack on. Let's have a go at finding angle BAD, okay? Well, if we just have a look at our triangle first, so we've got an apparent triangle here, okay? If we just have a look at the triangle, we can see that the base of this triangle is a diameter of the circle, okay? And I know it's a diameter because it goes through the center of the circle. So what we're looking at is a triangle in a semicircle. Now, all triangles in a semicircle are right angle triangles. So I can confidently draw a right angle symbol up there, okay? So now I know that BAD is a right angle triangle. Angles in a triangle add up to 180 degrees. So I know that angle BAD plus 55 degrees plus 90 will give me my answer, okay? So just jot this down quickly. So BAD plus 55 degrees plus 90 degrees equals 180. So BAD plus 145 equals 180 degrees. Put the degrees in. And we'll, rather than drawing the final step out, BAD is equal to 35 degrees. Okay. So we've answered the first one. We've got 35 degrees there. Good stuff. Now, if we're going to answer the triangle BCD now, so we're looking at the purple angle now. So let's have a look at some facts. Well, if we look at the line AC, I can see that line AC is a straight line. And if we have a straight line, and we can see we've got a line joining it from DB as well, it looks like I'm going to have another right angle here, okay? So I'm happy with that. I got another right angle there, which is good because that line seems to be coming off perpendicularly to it. So we've got another right angle there now. And now the angle BDC, now we don't quite know what that is yet. We're not quite sure what this angle in the corner is. But if we have a quick look at, if we look at the bigger picture, I can see that we've got essentially a radius coming from the center to the tangent line CD, okay? So that tells me that we have another right angle in here as well, okay? So to find this angle BDC, this blue angle in the bottom down here, it's going to be something plus 55 is equal to 90 degrees. Okay, so first of all, we're just going to do BDC first. So BDC plus 55 degrees equals 90 degrees. Therefore, BDC has to equal 35 degrees. Okay, so I know that this angle down here is 35 degrees as well, but that's not what we're trying to find. We're trying to find angle BDC. And again, we've got another right angle triangle in here now. So all triangles add up to 180 degrees. So our missing angle BCD plus 35 plus 90 has to equal 180. So BCD plus 35 plus 90 equals 180 degrees. So BCD plus 125 equals 180 degrees. So therefore, BCD has to equal 55 degrees. Okay, and that's our final answer for this question. Okay, so there's lots of steps in these questions. Okay, so each step individually is not too bad, but as long as you remember the key rules, the angles in a triangle equal 180 degrees, and you can spot all the hidden right angles in all these shapes, then you'll be absolutely fine. Okay, so let's jump into the first warm-up task. So looking at these diagrams, have a think which of these circles show us, or we can use the rule that angles between a tangent and a radius are 90 degrees. Okay, so pause the video, have a think which of these circles can we apply this rule to. Okay, so if we look at this first circle in the top left, it looks like we've got a tangent line and we've got the radius joining to it, and it looks like a pretty obvious tangent line. They're not going to try and trick you in the exam. It'll be blatantly obvious if it is or isn't a tangent line. Okay, so this looks pretty good. We've got a radius meeting a tangent at 1 point. Fantastic. If we look at the second one, just down right from it here, now we've got a line going through the circle. Now we do have the radius joining the line at 1 point where it touches the circle, but this line can't be a radius because it touches the circle at 2 points. Okay, so can't use it on this circle. Okay, what about the next diagram up and right from there? Now we've got a line and it does seem to touch the circle at 1 point, so you may start to think that it is a tangent line, but actually if we continued this line, we can clearly see that it would touch the circle at 2 points. Okay, so this is a no-go. We can't use our new rule on this circle. Okay, and the last one going down and right again, we've got a nice tangent line. It looks like it touched the circle once, and we've got a radius joining to it. I'm happy that we can use our tangent rule on this circle. Okay, so here's the first proper main task. Here it comes. So here's the main task. There's lots of different angles to find now, so make sure you read the angles carefully, so you make sure you answer the right one, make sure you're trying to find the right angles. Okay, and when you're drawing your diagrams, take real care to make sure you label everything up nice and clearly for yourself. Okay, so pause the video and have a go. Okay, here are the answers. So there was a lot of steps to do these. Okay, but as long as you work through step by step and you kept your diagrams fairly simple, hopefully you got these angles. Okay, now so let's have a look at the second circle theorem of the lesson. And this circle theorem says tangents to a circle from an external point to the points of contact are equal in length. Now this it sounds complicated, but unfortunately there's not an easy way to simplify this. The best I could come up with was tangents of a circle with the same starting point will be the same length. Okay, and what that means is if we've got an external point outside the circle, so we had point T, and we've got two lines coming from point T, and they're both tangents because they only touch the circle once. The distances, so for the first one, so TA, and the second one, TB, they would be the same length. Okay, no matter where this starting point is, as long as the lines coming from the starting point are tangent to the circle, they will be exactly the same length. Okay, And you can see that using these double lines through the tangents. Okay, that means they're the same length. Okay, and you can also see the radiuses meeting these tangent lines will also be the same length. The radius is not the same length of the tangent, so they'll be the same length as the other radius, because a circle's radius is a circle's radius, so that can't change length. Okay. And just a little bonus circle theorem, if you were to draw a line from this external point T to the center of the circle, you would bisect the angle between the tangents. Now, what does that mean? What that basically means is if I draw a line connecting the outside point to the center of the circle, it will split the angle between the tangents in half. Okay, that's what bisect means. It means to cut in half. Okay, so if you see a line from the external point go into the center, you know that you've got half of the bigger angle in one of those sections. Okay, let's have a look at some example questions for this topic. So we're given the angle of BDC is 18 degrees. We can see on the diagram we've got angle BDC, and we need to find the angle ADC. Okay, so let's have a quick look to find what ADC is. So I've got A, D, and C. So actually we're looking for the big angle, okay, the angle between both the tangents. Okay, now if you remember the last little bonus rule I gave you, the angle between if you draw a line from the external point to the center of the circle, you will bisect the angle between the tangents. Okay, so therefore if this angle up here is 18 degrees, then that means that this angle next to it also has to be 18 degrees because we've cut it in half. Okay, therefore ADC has to be the sum of 18 and 18. Okay, so ADC equals 18 degrees plus 18 degrees, or 18 times 2, whichever you prefer, and that equals 36 degrees. Okay, just like that. Let's have a look at another example question. So we're asked to find the size of the missing angle in this shape. Okay, so it looks like we've got two tangent lines coming from point B, and we're given the angle within the circle between the two radii. Okay, so we're trying to find angle ABC. So ABC, trying to find the angle in the nook of B. Now, how can we do this? There doesn't seem to be very much information going on here, but if we remember the first rule of the lesson, that angles between a radius and a tangent are right angle degrees, we can actually draw in we can actually fill in a lot more information for this diagram. So for example, if I look at the bottom here between D and C, I've got a radius meeting a tangent. So that must mean that this angle is a 90-degree angle. And if I have a look at DA, I've got another radius joining a tangent. So that means that has to be a right angle as well. And I've got a four-sided shape, I've got a quadrilateral, and all angles in quadrilaterals add up to 360 degrees. So angle in, it's not a four-sided shape at all. 1, 2, 3, 4, it's close enough. Angle in a quadrilateral equals 360 degrees. So therefore ABC plus 135 plus 90 plus 90 have to equal 360 degrees. Okay, if you add those up, ABC plus, or quickly, 135 plus 180 plus 360, ABC plus 315 equals 360. Therefore, ABC has to equal 45 degrees. Okay. So again, we're using rules now from the first circle theorem of the lesson to help us find these missing angles in these diagrams. Okay, so 45 degrees. Okay. Now let's look at one more example. Okay. So we're told that a circle has the radius of the circle is 3 centimeters, and point C is where the line BC touches the circle. Okay, So it looks like we've got two tangents. The line AB is a tangent and the line BC is a tangent. Okay. So we're told that point C is where the tangent meets the circle. Okay. And we're asked to find lengths AB. So let's color code this. AB, which is this line. And we're also trying to find BC, which is this line. And we're told the radius of the circle is 3 centimeters. So let's just finish labeling this up. 3 centimeters. Okay. Well, first things first, let's have a look at the what other lines can we draw in to sort of complete this picture? Well, if we're told that point C is where the line BC touches the circle, we can draw a radius to that point. So let's draw a radius out to point C. And what do we know about the lines between the angle between a radius and a tangent? Well, it has to be 90 degrees. So I've got a lovely right angle there. But also point D to point A is also a radius to a tangent. So that has to be a right angle there. Now, what is this missing angle at point D going to be between A and C? So angled ADC, sorry. What angle could that be? Well, it's a quadrilateral, so they all have to add up to 360. And if we've already got 390 degrees, that must mean that this angle has to be another right angle. Okay? Now, hang on a minute. We've got a shape that's got it's got 4 right angles, and two sides of the shape. One of them is 3 centimeters because it's a radius, and we've got another radius, which is also 3 centimeters. So what we're looking at here is actually a square, because it's got 4 right angles. So we know each the angles are the same. 2 of the sides are 3 centimeters, and they're not parallel sides. So that means that line AB has to be 3 centimeters, and so does line BC have to be 3 centimeters as well. Okay, so the only way the shape can possibly work, if we know that 2 sides, a vertical or horizontal side, are 3 centimeters, that must mean the other 2 sides have to be 3 centimeters as well. Okay, so BC equals 3 centimeters, and AB also equals 3 centimeters as well. Okay, so here comes the second warm-up task. Okay, so which of these circles show that tangents of a circle from the same external point have the same length? Okay, so pause the video and have a think which ones you think do and don't follow the rule. Okay, okay, so if we look at the first one on the left here, so we've got a circle, we've got 2 lines coming from an external point. And like I said, the examiner's not going to try and trick you. He's not going to draw a line so close, but actually it isn't a tangent. Okay, so we've got 2 lines. They look like they're tangent to circles. We've got radiuses joining them. Yep, I'm happy. We could use the rule on this circle. Moving on, one over now, one to the right. Now, this one, I know they said they would make it obvious. And if you were to look at the circle, you were to draw a line, it's blatantly, we were to continue this line, we can blatantly see that these are not tangent lines. Okay, they don't just about touch the surface, they're very much pointing straight through the circle. Okay, so unfortunately with this circle, because they're not tangent lines, we can't use our rule for this. Okay, if we move again, one over to the right now, to the third one, well, we can see we've got an external point, and these do look like tangent lines. If we were to continue these, I'd say that only touches the circle at one point. So that's, yep, they're both tangent lines, and they're from the same external point. So we can use this shape with the rule. And now the final one, number 4, well, we can blatantly see these aren't tangent lines because they're cutting straight through the shape. Okay, so even though they do look like they're roughly the same size, because they're not tangents, we can't tell for certain. Okay, so this last one doesn't follow the rules because they're not tangents. Okay, so let's have a look at the final main task of the lesson. Okay, so it's a lot of information to take in. Pause the video. You might have to think a little bit outside the box for some of these questions. Okay, so pause the video and have a go with them. Best of luck. Okay, so here are the answers. So the first one was very much like one of the examples. The second question wasn't like any of the examples. It was a little bit of a trick question, unfortunately, but it was you had to use Pythagoras to figure out the missing side WX, and then you could find out the whole perimeter of the red shape by adding them all together, knowing that they're the same side. And then question C was very similar to the last example I gave you, where we ended up having a cube. If you join tangents and radiuses together, you end up getting a cube, and you have to join that missing. You had to find the missing length C, which ended up being 8 centimeters. Okay, so if you got that last question C, very well done. That was a slightly trickier one, that one. Okay, let's have a look at the final checking question. So final checking question of the lesson now. So using the given angle, we need to find the size of angle X, okay? So we need to find angle X at the bottom of the shape, and all you're given is one angle 22 in one part of the top part of the shape. Okay, so pause the video and have a go at this checking question. Okay, best of luck. Okay, so let's work through this example. Okay, so first of all, so we're given an angle 22, we're trying to find angle X. Okay, so let's find out what information we can. Okay, well, if you remember, a line if we have two tangents coming from an external point, a line from that external point to the center of the circle will bisect the angle between the tangents. Okay, so that means that we are able to find out the angle next to this angle 22, because it will also be 22 degrees. Okay, now the next step, I'm just going to get rid of some stuff here now. The next step is to find this angle at the opposite. We're going to find this angle opposite the two tangents. Okay, well, how can we do that? Well, if we know both those angles up there are 22, that must mean, make sure big blue, that must mean that both the angles together are 44 degrees. Okay, so now we're trying to find the purple angle at the bottom, at the opposite that angle. Okay, and because we've got radiuses meeting tangents on the left and on the right here, that must mean that we've got two right angles here. Okay, so, and if we look at the whole shape now, we've got a quadrilateral going on here. So we're going to let's call the purple angle Y for now. So Y plus 90 plus 90 plus 44 equals 360. And you should have found that Y is equal to 136 degrees. Okay, so we can cross out there. So Y equals 136 degrees. Okay, now we've run out of other angles that we can find using the rule from this lesson, but there was one rule from the very first circle theorem lesson that should help you find angle X. Okay, and that is the angles at the center of circles are twice as big as the angles at the edge of a circle. Okay, so I know that angle X is equal to half of 136. Okay, so if you halve 136, you get 50, 65, 68 degrees. Okay, and there you go. That's the final checking question for the lesson. So that's using the latest circle theorems you've learned today, and also a circle theorem from the very first lesson as well. Okay, so very well done if you got that question right on your own. And well, the last lesson is on alternate segments, okay, which is the trickiest one of the bunch. Okay, so we'll see you then. Okay, bye now.